Question number 1. A gas mixture containing CH4, C2H6 and excess O2 was introduced into an evacuated, closed, rigid container. The volume of the container was 8.314 into 10 to the power minus 3 cubic meters. The pressure of the container at 400 Kelvin was 4.8 10 to the power 6 Pascal. Calculate the total number of moles of gases in the container. Assume that all the gases behave ideally and that there is no reaction at this temperature. There are 3 gases inserted into the given container. The volume of the container, temperature, and the total pressure inside the container were given. And we have to calculate the total number of moles. For that, we can use the ideal gas equation. PV equals nRT. And we have to calculate number of moles. Therefore, when N is the subject, PV divided by RT. Total pressure 4.8 10 to the power 6 Pascal. Volume of the container 8.314 10 to the power minus 3 cubic meters. R 8.314 joules per Kelvin per mole. It's given in the paper. Temperature 400 Kelvin. Then you will get the answer. Total number of moles in the given system is 12 moles. Question number 2. All the hydrocarbons in the container were completely combusted by increasing the temperature of the container to 800 Kelvin. The pressure of the container after the combustion reactions at 800 Kelvin was 1 into 10 to the power 7 Pascal. Calculate the total number of moles of gases in the container after combustion. Assume that H2O is present as a gas under these conditions. We know that when the temperature is 800 Kelvin, water exists as water vapor. Initially, at 400 Kelvin, CH4 gas, C2H6 gas and excess O2 gas were present. And these are hydrocarbons. In the presence of excess oxygen, when these two hydrocarbons undergo complete combustion, carbon converts to CO2, hydrogen converts to water. And therefore, at 800 Kelvin, remaining oxygen gas was present in the container. Then this total pressure is due to the produced carbon dioxide, produced H2O gas and the remaining oxygen gas. Now we need to calculate the total number of moles in this system. For that we can use the ideal gas equation. Number of moles is PV over RT. Again, the total pressure was given and we have to calculate the total number of moles. Pressure 1 into 10 to the power 7 Pascal. Volume is the same because it's a rigid container. 8.314 10 to the power minus 3 cubic meters. Next R 8.314 joules per Kelvin per mole. Temperature is 800 Kelvin. Now simplify these values. You will get the answer 12.5 moles. Question number 3. Write balanced chemical equations giving physical states at 800 Kelvin for the combustion reactions of the gases given below. Then we know these are hydrocarbons which contains carbon and hydrogen. When they undergo combustion reactions or when they combusted in the presence of excess oxygen, carbon converts to carbon dioxide and hydrogen converts to water. Carbon dioxide is a gas. At 800 Kelvin, H2O exists in the gaseous state. Combustion reaction for methane, CH4 gas with excess O2 gas. It produces carbon dioxide gas and H2O gas. The reason is temperature is 800 Kelvin. And you have to indicate the physical states as well. Now balance the given reaction. 2 and 2. Combustion equation for C2H6 gas. C2H6 with excess O2 gas produce CO2 gas and H2O gas. Balance the reaction. 2 carbon dioxide, 3 H2O. The question asks you to write the balanced chemical equation for the combustion. Therefore, it's better if you can remove these fractions. So you can see, if you can multiply the whole equation by 2, you can get rid of this fraction. Therefore, we will multiply the second equation by 2. You will get 2 C2H6 gas, 7 O2 gas, 4 CO2 gas, 6 H2O gas. This is the answer for the question number 3. Question number 4. Only one of the two hydrocarbons above contributes to the change in the number of moles of gases before and after combustion. Calculate the number of moles of this hydrocarbon initially introduced into the container. We know there are two hydrocarbons, CH4 gas and C2H6 gas, and we need to find out which one contributes to the increase in number of moles after the combustion. To continue, we need the equations we have written for the question number 3. Now we will consider number of moles of CH4 gas in the initial container as X moles. Then number of moles of C2H6 gas in the initial mixture as Y moles. According to the stoichiometry, CH4X gas was present. Then for the complete combustion of CH4 gas, we need 2X moles of O2 gas, because the stoichiometry we can see 1:2. And then the produced amount of carbon dioxide from the combustion of methane, it's X moles. Stoichiometry 1:1. Then again water, stoichiometry 1:2. Therefore, the produced number of moles of H2O gas is 2X moles. Now we will move to the second equation. Stoichiometry between C2H6 and O2 is 2:7. If 2 moles of C2H6 present, we need 7 moles of O2. Then if 1 mole of C2H6 is present, it's half, that is 3.5 moles of O2 required with 2 moles of C2H6. Therefore, we need 3.5 Y moles. Now move to the product side. C2H6 and carbon dioxide, it's 2:4 means 1:2, so it's 2Y. Then water, H2O gas, again 1:3 stoichiometry, then 3Y moles of H2O gas was produced. Now check the number of moles in the reactant side and the product side. We can see methane 3x moles of reactants are present and 3x moles of products have been produced. 3x moles have been reacted and 3x moles have been produced. Therefore, the first reaction, it doesn't increase the number of moles of gases. Now move to the second. Y plus 3.5y. So you can see it's 4.5y moles initially present. Finally, it's 2y plus 3y, 5y moles. Now this clearly explains you during the second reaction, number of moles of the gaseous products have been increased. Therefore, that is the answer for the first part, because you have to find out the gaseous hydrocarbon which increases the number of moles of gases after the combustion. Therefore, you can write C2H6 gas contributes to the change in the number of moles of gases before and after combustion. Now move to the calculation part. Calculate the number of moles of this hydrocarbon initially introduced into the container. C2H6 is the hydrocarbon which contributes to the change in the number of moles of gases before and after combustion. You have to calculate the numerical value of Y. Initially, X moles of CH4 gas and Y moles of C2H6 gas were introduced into the container. Then, excess amount of O2 also introduced into the same container. Now we have to find the total number of moles of O2 initially introduced into the container. 2x for the complete combustion of CH4 gas. Then 3.5y, that is for the complete combustion of C2H6 gas. And then the remaining oxygen, because we know excess amount of O2 have been added. So we have to indicate that as well. We will write it as NO2, right? So this is the remaining amount. So this indicates the total number of moles of O2 present in the initial container. And then we know the total value. If you add all these three number of moles, the answer is 12 moles. Now move to the product side. Carbon dioxide, X moles have been produced from CH4, 2Y moles have been produced from C2H6. So this is the number of moles of carbon dioxide, that is X plus 2Y moles. Then the total number of moles of H2O gas. 2X moles have been produced from CH4 gas. 3Y moles have been produced from C2H6 gas. Therefore, total number of moles of H2O gas is 2x plus 3y moles. And then the remaining oxygen, that is NO2. We know the total value, the total number of moles of these three gases, that is 12.5 moles. Therefore, we can write two equations. Initial number of moles of CH4 gas plus initial number of moles of C2H6 gas plus initial number of moles of O2. We can write it is the total oxygen equals 12. Number of moles of CH4, that is X moles. C2H6, it's Y moles. Oxygen, it's 2X plus 3.5Y plus NO2. That is the remaining amount. That equals 12. 3x plus 4.5y plus NO2 equals 12. This is the equation 1. Now we can do the same for the final mixture. Number of moles of produced carbon dioxide plus number of moles of produced water vapor plus number of moles of O2 remaining equals 12.5. Number of moles of carbon dioxide, that is X plus 2y. Then number of moles of H2O gas produced, that is 2x plus 3y. Then number of moles of remaining oxygen, we use the symbol NO2. It's 12.5. 3x plus 5y plus NO2 equals 12.5. This is the second equation. 2 minus 1 gives you the answer 0.5y equals 0.5. Therefore, y equals 1 moles. In other words, number of moles of C2H6 equals 1 mole. So, this is the initial number of moles of C2H6. Question number 5. The container was then cooled to 300 Kelvin and the water was removed. Then the pressure of the container was 2.1 10 to the power 6 Pascal. Calculate the following. Here we have the system at 800 Kelvin. So that's the previous part. What's inside the system was the produced carbon dioxide gas, produced water vapor, and the remaining oxygen. So this is at 800 Kelvin temperature. Now the temperature has been reduced to 300 Kelvin. It's the same as 27 degrees Celsius. We know at this temperature water vapor condenses to liquid water, and then it says water was removed. Now, the gaseous species inside the system was CO2 gas and the remaining oxygen. The total pressure. The pressure is because of these two gases. And then, during part 1, we need to calculate the total number of moles of H2O produced. Now, we know the total number of moles of gases in the previous system, that is 12.5 moles. 12.5 moles means produced carbon dioxide gas, produced water vapor, and the remaining oxygen. Then if you find in total in the system at 300 Kelvin, it gives you the total of CO2 gas and the remaining oxygen. Then you can see 12.5 minus this answer gives you the number of moles of H2O produced. Now, first we will calculate in total at 300 Kelvin. Is PV divided by RT. Then we will substitute values. Pressure 2.1 10 to the power 6 Pascal. Volume 8.314 10 to the power minus 3 cubic meters. Value of R 8.314 joules per Kelvin per mole, and temperature was 300 Kelvin. You will get the answer as 7 moles. Number of moles of H2O is the in total at 800 Kelvin, it's 12.5 moles, and now it's 7 moles. This difference gives you the answer. So the number of moles of H2O produced is 5.5 moles. Part 2 of question number 5. Number of moles of H2O produced from the combustion of C2H6. From the previous question, we have calculated the initial number of moles of C2H6 gas, that is 1 mole. Now we have to calculate the number of moles of H2O produced from C2H6. Now you can see it's 3Y moles. Therefore, number of moles of H2O gas produced from the combustion of C2H6 gas is 3 moles. Question number 5, part 3. Number of moles of H2O produced from the combustion of CH4. Total number of moles of H2O produced is 5.5 moles. Then, number of moles of H2O produced from C2H6 is 3 moles. Therefore, we can calculate the number of moles of H2O produced from methane. It's 5.5 moles subtract 3 moles. Therefore, the answer is 2.5 moles. Question number 5, part 4. Number of moles of O2 introduced initially into the container. We know the number of moles of C2H6 present in the initial mixture because we have calculated earlier. It's 1 moles. Then, if you know the number of moles of initial CH4, we can calculate the number of moles of initially introduced oxygen. Therefore, first we need to calculate the initial number of moles of CH4. Number of moles of H2O gas produced from the complete combustion of CH4 has been calculated earlier. Therefore, 2x equals 2.5 moles. Then from that we can calculate the value of x. It's the half, and that is the number of moles of methane initially present in the mixture. Therefore, we can write number of moles of methane in the initial mixture as 1.25 moles. Next, we will write the relationship between these three. We know the total number of moles present initially, that is 12 moles. Therefore, number of moles of methane, initial number of moles of C2H6 plus initial number of moles of O2 equals 12 moles. Then substitute values. Methane, it's 1.25 moles. C2H6, it's 1 mole plus number of moles of initial oxygen, total equals to 12 moles. Initial number of moles, it's 9.75 moles.